students. Again, we are back with SN reaction mechanisms. That is lecture 6, part 6 of halogen derivatives. I have just given you a primary idea about substitution nucleophilic reactions, right? We have to go into the details of both the reaction mechanisms SN1 and SN2. Very, very important, the base of organic chemistry, right? Uh, Almost all the question papers have a broad answer type question on this particular subtopic, right? So last time we have seen substitution nucleophilic reactions, the mechanism, how it proceeds. Now we have to go into details into each type of SN reaction mechanisms. We will right now start with SN2. It's like this, SN and then 2. You can call this SN2 reaction, you can call this SN2 reaction, and the whole mechanism to be studied. SN2 reaction mechanism. Very, very important. See that you have your notebook with you. Each point that I will be explaining will be noteworthy. You have to note it down. So see that you have your notebook, your pencil, your whatever, textbook if you have, it's well and good. You can mark the important points there also. What is the meaning of this? This would be better understood if we take an example, or we can say that hydrolysis of primary alkyl halide. We are talking about SN2 reaction mechanism. Again, I said we have to focus on alkyl halides. So it is given that hydrolysis of methyl bromide, a simple alkyl halide, okay, when in presence of a suitable solvent, it gives you the product, that is CH3OH, methyl alcohol, plus Br. You can call it KBr as the byproduct, or simply even if you say it is Br minus, it is just okay. So this is substitution nucleophilic reaction. One nucleophile being replaced for the other nucleophile. Correct? So substitution reaction by a nucleophile, so substitution nucleophilic. But again, that term we have to see. 2 stands for what? Now, this hydrolysis of a primary alkyl halide, first degree alkyl halide. Here, what is the degree of carbon atom here? It is 1, isn't it? Because it is attached to 3 hydrogen, no other carbon atom. Primary alkyl halide. The rate of this chemical kinetics, if you have studied about chemical kinetics, in chemical kinetics, the rate of the reaction is to be determined. It is found for this particular reaction that the rate of the reaction is directly proportional to the concentration of the substrate, 2 molecules CH3Br, and also on the concentration of the nucleophile, that is OH minus ion. Correct? So rate of the reaction, it is experimentally found. This is experimentally found. Rate of the reaction is directly proportional to the concentration of the substrate CH3Br and also to the concentration of the nucleophile taking part in the reaction. Right? Now, since two molecules are involved in determining the rate of the reaction, correct? In determining the rate of the reaction, you can say that this is substitution nucleophilic bimolecular reaction. Substitution nucleophilic bimolecular. What does this mean? That the molecularity of this reaction is 2, whereas order also is 2, second order reaction. Now the terms molecularity and order we have studied in chemical kinetics. But since two molecules are involved in the rate determining step, they are involved in determining the rate of the reaction, we can say that this particular nucleophilic substitution reaction is also bimolecular. And therefore we write it as SN2. This S, small little below we write, and then substitution nucleophilic, 2 stands for its molecularity and it is bimolecular. Right? So first, kinetics, experimentally found. Now we go to the actual mechanism. How does the mechanism take place? Alright. Now, I will draw this C. Okay. H. I can draw this and draw this 3 hydrogen. Then you have this Br. You have this, okay. This is the substrate. Now suppose hydrolysis means, what is hydrolysis? Reaction with water, hydrolysis, breaking. So this you can see that in this case CH3Br, this bond is polar. Why? Due to the electronegativity difference. Br is pulling the electron pair toward itself. Alright, and therefore what is happening? Partial positive, partial negative charges will be developed. The process of bond breaking will not be complete, but the charges will be shared by these two. Right? Now, when hydrolysis takes place, that is the attack of the nucleophile, OH minus. This will attack the carbon from the side, the rear side, back side. Correct? Rear side, back side. And then the Br will leave as the living group. But this is taking place simultaneously, right? So we show like this. Of course, I will tell you with solvent, how do you understand whether this is SN2 or SN1? I will be telling you, okay? Now, it will attack the carbon from the side that is opposite to the living group, and you will get somewhat this sort of a stage. C, H, 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 and then this OH, partial shown by dotted line, and this Br also shown by dotted line. What does this indicate? This that is formed is called as the transition state. This that is formed is called as the transition state. Why this is happening? Because we want the reaction to take place, isn't it? The substrate, that is CH3Br, is to be attacked by the nucleophile. But remember, which nucleophile now? Br is also a nucleophile. OH minus is also a nucleophile. I mean, OH, which is obtained by this from hydrolysis of, right? OH is also a nucleophile, but OH minus is comparatively a stronger nucleophile as compared to Br minus. And therefore, this Br will leave, correct? And OH will, at the same time, it will attack the carbon, where at that point where that Br has left. And then you will get this condition of carbon, where carbon is in this state, it is highly unstable. This is the highly unstable state. Highly unstable. Correct? And the partial negative charge, okay, or minus half you can show, or we also show it like this. In this condition, the carbon is pentacoordinate. Pentacoordinate. What does that mean? Carbon is attached to 1, 2, 3, 4, 5. Is that possible? Carbon having valency 5? No, because carbon is always tetravalent and this condition should not exist. It is highly unstable. And then immediately what will happen? This will break down to form the product, that is C, H, and OH. Of course, what will happen? This will leave plus Br minus. What is this called? This is called as the product. And what is this? This is the leaving, LEA. It will leave, leaving group. This is the leaving group. Alright, so this is the mechanism of the reaction. Mechanism in short, but I will be explaining it once again. Hydrolysis of methyl bromide, primary alkyl halide, undergoes hydrolysis, breaking. Which bond will break now? The bond between C and Br will break, and the bond between C and OH will be formed completely. This is also a nucleophile. This is also a nucleophile. One nucleophile substituted by the other. But in this case, this is a weak nucleophile. This is a strong nucleophile. So what is must for SN2 so that the nucleophile can be replaced is that the attacking nucleophile should be stronger than the leaving nucleophile. Until and unless, then you will not get this whole procedure. Alright. Now, it is experimentally found that the rate of the chemical kinetics of states that the rate of the reaction, this particular reaction, is directly proportional to the concentration of two molecules, that is the substrate and the nucleophile. Since the rate of the reaction depends upon two molecules, therefore we call it as substitution nucleophilic bimolecular reaction. The actual mechanism is that OH minus, being a strong nucleophile, what will happen now? This, I told you, CBr bond is polar. Br is pulling the electron pair towards itself, right? And so since it is more electronegative than carbon, it is pulling the electron pair towards itself. It wants to free itself, you can say in short. It wants to free itself, and therefore it will try to loosen this bond, right? It will try to loosen this bond, and in that process it will try to make a certain place for the other nucleophile to attack that carbon, correct? So this bond will be weakened. So see here, so it is this bond, CBr bond has not been broken completely, all right, and therefore you show it by the dotted lines. At the same time, now since it is pulling the electron pair, what happens? This becomes positive, this becomes a partial positive, partial negative. Now this is the proper site where this nucleophile can attack. And so it will be in a, it will be finding out a chance to attack the carbon when this condition arises, correct? This bond is started becoming weak because it wants to free itself. It is pulling the electron, it wants to take away the electrons with it. And this is the right time when this nucleophile, the strong nucleophile, will attack this carbon. And this stage will be obtained. Okay, this is the intermediate state. This is called as the transition state. It is highly unstable. Why? Because carbon is in the penta-coordinate position. It is penta-coordinate and this is not possible. Did you follow it? So see, I have shown this wedge formula here. Correct? Now you can say that a minus half minus half. So if you don't, there will be distribution of the negative charge. Followed my point? Okay. And this bond breaking is not complete, whereas the bond formation is also not complete. But this will not remain in this condition for a longer time. It has to break down and form the product. And then we will get the product, which is CH3OH plus Br. But if you see my diagrams, my drawing is not too good, but even then, it is possible for you to understand. What is happening in this case now? The product that is formed with inversion of configuration. Inversion. It is like you take an umbrella. In the present position, the umbrella will be this type. But if you hold the umbrella against the direction of wind, it will be blown inside out. That is it. So in SN2, the product formed is with 100% inversion of configuration. We have done this in the optical activity part. And when can this be studied? When you have this compound being placed in, or you have a chiral carbon atom and all that possibilities. Okay? But even then, this could be the phenomena. 100% inversion of configuration. Why? Because the nucleophile OH minus, the attacking nucleophile, is attacking the substrate from the rear side, from the back side, from the side that is opposite to the living group, and therefore you have such a transition state which is highly unstable, which does not remain in this position for a longer time. It will break and you will get the product immediately. Now in this case, the attacking and the breaking, the attacking and the leaving of the nucleophile is simultaneous, and therefore we can say that SN2, all right, is a one-step reaction mechanism. The reaction takes place in one step reaction mechanism. Single step, correct? Single step. Got this? In this case, the bond angle between CH and OH or CHH will be 120. This carbon in this case is sp3 hybridized, sp2 hybridized. Here it is sp3 hybridized. Okay, so many changes you have to keep in mind. And the product that will be formed with 100% inversion of configuration. Tertiary butyl halide is undergoing hydrolysis, and if you write down the SN2 reaction mechanism, it is not correct. Why this particular first degree, why this is undergoing SN2? This is because, correct, in the intermediate step, there are to be 5 bonds. And you imagine if instead of these 3 hydrogen, there would be 3 CH3 groups, 3 CH3 bulky. And again, then you would have OH minus, you would have Br minus, correct? And then there would be a sharing of those charges. It would be such a bulky something that would be formed. And in this case, in the intermediate, no carbocation is formed. And therefore, since the intermediate is formed as a transition state, you can say that this is one step reaction where the attack takes place from the side that is opposite to the living group, and the product so formed is formed with 100% inversion of configuration. It is just like I told you, the umbrella turning inside out, correct? And that configuration was also studied by Walden, and therefore it is also called as Walden inversion. So these are the peculiarities of SN2 reaction mechanism. Of course, the solvent that we have to use for carrying out this reaction mechanism is always polar aprotic solvent. Polar aprotic solvent. See, MCQ type of question. Solvent is given. If it is polar aprotic and you say it is SN1, it is wrong. Remember that SN2 is favored or is possible for when the solvent that we use for hydrolysis is polar aprotic. Correct? And I told you polar aprotic solvents like you have acetone, correct? Then you have those DMSO, dimethyl sulfur oxide, correct? And so many others. So if those solvents are used, then only SN2 reaction mechanism takes place.